In this session, we'll be looking at Dijkstra's algorithm to solve single source shortest paths problem. We'll use a greedy approach to solve this problem. Just to recap, greedy technique involves three major steps. At each step, you will check whether the solution is feasible. The second, which you will check, is whether it is locally optimal. And the last is once you have made a decision, it is irrevocable. So these are the three main steps in a greedy approach. We have looked at Prim's and Kruskal's algorithm in our earlier classes. Now we look at Dijkstra's algorithm. Now, what do you mean by single source shortest path? Basically, you have a source, you have a vertex. From that vertex, you are required to find the shortest path to all its other vertices. Right? It's a weighted connected graph. One of the important criteria for Dijkstra's algorithm is it's applicable to both directed and undirected graphs and non-negative weights only, which means that weights has to be positive. So the objective is clear. I need to find the shortest path from a given vertex, which is called as source, to all its other vertices. Now let's look at the algorithm on how it works. Now basically what you do is at every stage you choose the vertex, right, which is nearest. So in simple terms, what we do is from the source vertex, it finds the shortest path from the source to the vertex nearest to it, and that vertex is chosen. The same step is repeated for the second vertex, third vertex, and so on until all the vertex shortest path are found. So it basically identifies the shortest paths to I minus 1 or n minus 1 vertices. Let's look at the example here. So now this is a undirected graph. You have 5 vertex A, B, C, D, E. Now my task is to find out the shortest path. For this example, we'll consider A as the source vertex. So if you look at here, to begin with, I've considered A. So the remaining vertex are B, C, D, E. So the direct edge are with B and D. So to begin with, I'll update both the values B and D directly. So that's the first step which I'll be doing. B and D are updated. So A to B is 3 and A to D is 7. So the way I write is B A comma 3. Whereas the other vertex C and E are not reachable. So my first task here is to choose the one with the least cost. So between 3 and 7, the least is 3. So 3 is added to the vertex, which is already as A, and here we have highlighted AB. Now in the next step, what I need to do is, I need to also consider the remaining vertex here. So the remaining vertex are C, D and E. Now coming to C, the previous value was infinity. If you look at here, it is infinity. Now, in this step, I am looking at whether there is a path from A to B and then to C. So here what we do is, since I am finding shortest path from A, I have already chosen vertex AB. So AB is 3. So when I compute the distance, I will be adding this 3 here and then the actual edge cost. So to C, my previous chosen value is 3. So 3 plus B to C is 4. 3 plus 4 is 7. So this new value should be less than the previous value. So earlier value was infinity. Here it is 3 plus 4. So 3 plus 4 is updated here. Now come to D. What's the previous value? 7, which means that there is a direct path from A to D with a value 7. Now what if I go through A to B and then B to D? So I'll add the previous, which is 3, plus B to D is 2. So B to D is 2 and previous is 3. So 3 plus 2 is 5, which is better than the previous value, which is 7. So hence I'll update it. So I'll replace 7, which was a direct path from A to D, with B, which is 3 plus 2. E from B is not reachable, so it remains the same. So among this, between this 7 and 5, 3 plus 4, 7 and 3 plus 2, 5, the least is 5. So 5 is selected here. So 5 is selected and the chosen vertex is D. So path A, B, D is selected now. 3, 2, 3 plus 2, 5. That's what the new value 5 is. Now, if you look at what are the remaining vertex, C and E. So, C, the previous value is 7. If I consider it through B, what's the value here? This value is 5, right? 5 plus 5, D to C. 5 plus 5 is 10. But then the previous value 7 is less than 10. So I'll retain the old value here. Okay. So please understand C, I can go from D to C, which is 5. I'll add 5 to previous. 5 plus 5 is 10. But then 10 is not better than the previous value. So I'll retain the previous value. Now to E. So D to E, there is a path. So what's the previous value? 5. 5 plus 4, 9. But the previous value is infinity. So 9 is better than infinity. So I'll update here. So between 7 and 9, which is less? 7. So C, B, comma 7 is chosen. Now the remaining vertex is E. So previous is 7. C to E, there is a path with value 6. So 7 plus 6 is 13, right? 7 plus 6 is 13, but the previous value is 9, which is better. So I'll retain E of D comma 9 here. So this is also selected. Now the path chosen is, to begin with, A to B, highlighted here, B to D, B to D, D to C, right? D to C, right? And then D to B, BD, and then you have selected C, that is BC here, 4, and then E, D to E, right? So these are the edges selected. Now, how do you find the shortest path from this? It's quite simple. What you need to do is, let's say from A to B, right? I need to find A to B. So go to B. What is the vertex here? A. So go back to A. You get A. So A to B is 3. Now A to D, right? Go to D. So D is what? D from B. Now go to B. B is from A. Go back to A. So you have A, B and D. So D to B, B to A. So the total cost is 5, ABD. Now how do you find for C? Go to C. What is C? Previous vertex is B. B, what's the previous vertex? A. So the path is ABC and the cost is 7. Similarly for E, go to E. What's the previous vertex? D. Go to D. What's the previous vertex? B. What's the previous vertex? A. So you have A, B, D, E with a length of 9. So this is how Dijkstra's algorithm works. Again, it's a greedy technique. At each stage, I choose a solution which is feasible, optimal. Here it is optimal, the least cost. And then once I have chosen, it is irrevocable. So it means that I cannot go back to the previous step. So every stage I keep incrementally building the solution in a greedy manner. Now, how does the algorithm work? Right? So the algorithm makes use of a priority queue. The priority queue is used to remove the edge with the shortest value, right? So we look at that. So what I will be doing here is basically I will be initializing the vertex, right? So dv, all the vertex will be initialized to infinity. PV is refers to the previous vertex visited, which is null. Then I will be adding that into the queue. Then what I'll do is I'll be beginning the process. S is the source vertex. So initially source vertex value of D would be 0. I'll be updating it here. And then initially the edges selected is null. So what I'll be doing is I'll be going through each of the vertices 0 to V minus 1. Pick the smallest value from the queue, which is the edge. Add that edge to VT. And from that edge, keep checking whichever the vertex which is adjacent to U star, apply the formula. Previous, that is this value plus the new cost value. If it is less than the earlier value, right, then update it and update the previous. Okay, then update the queue. Let's look at the example of how do you trace the algorithm here. I'll take the same example here. So initially, if you look at here, all the vertex, the same example, dv, everything is set to infinity here to begin with, and then pv is all set to null, and then here ds is set to 0. What's the source vertex here? S is a, so dA is set to 0. So initially vt is null, no edges are selected. Now coming to the second part of the algorithm, where I need to update the values of db, dc, dd and de, right? So again, as I told you, like we'll pick the least edge, add it, from that again initiate the process, check if the new value is better than the previous value. If it is, then update the value, then update the pu here as well. So now the first step, delete minimum. So which is the minimum here? 0. So dA is chosen, right? Now from that vertex u star, okay, from that vertex u star, I'll initiate the process, right? So u star is a, right? Now vt a gets added. So du star, that is dA is 0. Now I'll update this formula. Which are the vertex adjacent to a? So if you look at the graph here, adjacent to A is B and D. So what I'll do is I'll find DB and DD. So DX is what I have mentioned here. X is DB and D. So I'll apply the formula for DB and DD. The rest, as usual, it remains infinity. So what is DB? DB is nothing but I'll check if this is less than the old value. What was the old value of DB? If you look at here, it was infinity, dB and dd. Now when I apply this formula, right, when I apply this formula, so you can easily get that this is 0 plus, what's the new edge? U star is, remember A to B. So what is A to B here? A to B is 3. A to D is 7. So A to B is 3, then A to D is 7. So since infinity was the previous, 3 is better, 7 is better, so I have updated the value. Now next, choose the next least vertex value, right? Which is the least value? 3, which is B, right? Now I have picked B, which are the vertex which is adjacent to B, right? So the adjacent to vertex B are C and D. So if you look at the graph here, B, you have CD adjacent. Now you need to compute DC and DD, right? So DC and DD here. So DC and DD needs to be compared. If you look at the previous value, DD is 7. So DC, you have a edge which is directly visited. So that is B to C, the value gets updated here. So it's 7. Now come to DD. If you apply the same formula, you need to apply the same formula, substitute the values, you get it as 5, right? And then every step I am updating the previous value. Okay, so initially if you go back here, first time when I visited 3, the previous vertex is A. Now second time, DC, the previous vertex is B. The previous vertex 7, it was A. When I update it with 5, it becomes B. Then I becomes 2. Then I pick the next least value, which is 5 here. Then I'll update the table, update the previous vertex visited. Then I becomes 3. Then I pick C. So from C, I'll update the values here. I'll update the previous. And finally, the last vertex E is chosen. Update the values and stop it. So this gives you the shortest distance, which is 3759. And then this is same as what we highlighted while solving the problem. So this is how your algorithm works. You can trace the algorithm by taking an example and substituting the values for the formula. But this is how Dijkstra's algorithm works. The time efficiency, it depends on the data structure for implementing the priority queue and for representing the input graph. If you are representing it by adjacency list and priority queue is implemented as a minimum heap, min heap, then the complexity is given by big O of E log V. Various applications of the Dijkstra's algorithm, GIS, Geographic Information Systems, I need to find the shortest path, right? Say Google Map is a good example where it could be applied. While transferring packets from one node to another node, you can use Dijkstra's algorithm to find the shortest path. Find a network model in spreading of a fixed infectious disease application in biology. Telephone networks, cellular networks for routing, connection, and communication. That could be another application of Dijkstra's algorithm.